Good morning, guys. So today we're going to be going over our last lesson of chapter 3. So at the end of this lesson, I'll give you some homework. Tomorrow will be a day for you guys to do practice questions and to email me anything that you're having trouble with, anything that you still need an explanation for. And then the day after that will be your first quiz that we're going to be doing online. And there will be information on your Google Classroom about how that's going to work. And if you have any questions or concerns, you can, of course, email me about that as well. But today's lesson is going to be continuing on with the stuff that we were learning a while ago now, essentially the ACB method of factoring. So still factoring polynomials using the same kind of steps that we have been. These are just 3 different special types of polynomials that we're going to be talking about. So I'll go over one example for each of those 3 types, and then that'll be it. Okay, so the first type of special polynomial that we're going to be doing is the perfect square trinomial. So this is lesson 3.8, and it's essentially just all about factoring special polynomials. So again, the first type number 1, is our perfect square trinomials. What that looks like is something like this. What makes this a perfect square trinomial is that both the first and last term are perfect squares. So the square root of 4 is 2, the square root of x squared is x, the square root of 9 is 3. So both the first and last term are perfect squares. That's not going to change much. It's just going to make our final answer a little unique. And you'll see what I mean by that when we get there. We're still going to start with the same first step, though, which is multiplying our a value by our c value. So 4 times 9 is 36. And then our second step is still to find the factors of 36. So it includes things like 1 times 36 and 2 times 18 and 3 times 12 and 4 times 9 and 6 times 6. Then, of course, we have to pick which one of those pairs will add to our b value, in this case, positive 12. So that is, of course, 6 plus 6 will give us positive 12. From there, we're going to keep our first term, and our second term gets replaced with those factors. So positive 6x and positive 6x, and then our constant stays the same. Don't forget, when that center term gets replaced, we cannot lose our variables. We have to keep our x's. Then we're going to split this in half, like so, and factor each half individually. So if we look at 4x squared plus 6x, both the 4 and the 6 are divisible by 2, so I'll take a 2 out, and they both have an x, so I'll take an x out as well. And then I'll write what I'm left with in brackets. So 4x squared divided by 2x leaves me with 2x, because 4 divided by 2 is 2, and x squared divided by x is x. And then positive 6x divided by 2x leaves me with plus 3. I'll then do the same on the other side. So positive 6x and positive 9. I can take a 3 out of both of them. They're both divisible by 3. I cannot take an x out because there's no x here. So 6x divided by 3 leaves me with 2x, And positive 9 divided by 3 leaves me with plus 3. I then double check that my two binomials are the same, and I write them underneath. Right there. And then whatever's left outside of the bracket gets put in its own binomial. This is a positive 3, so we'll write plus 3, like so. That makes our second binomial. Now, what makes perfect square trinomials unique is that the fact that both of the binomials in my final answer are the same as each other. And so I actually write my final answer like so, 2x plus 3 squared, because I have 2x plus 3 times 2x plus 3. So anytime you have a perfect square trinomial, your final answer should be written as a power, like that. The second type of special polynomial is one that involves two variables. So the two-variable polynomial. The special rule when you're doing two-variable polynomials is that anytime you have two variables, the middle term must contain both variables. Okay, the middle term has to contain both the variables. If the center term doesn't have both variables, you need to rearrange the polynomial so that it does. So let's look at an example of that. 2a squared minus 3b squared minus 7ab. The very first thing I'm going to have to do is take this term here and move it to the middle so that my middle term has both variables. So I'll rewrite this as 2a squared minus 7ab minus 3b squared. Now our middle term has both the variables. Now we can essentially just follow the same steps that we have been using. So step number 1, a times c. So our a value is 2. Our c value in this case is negative 3. It's no longer our constant, but it is still our third term. So 2 times negative 3 gives us negative 6. Okay. Actually, sorry, forgive me. I'm going to change this to a positive 3, just to make things easier on us. The other thing that shows is don't forget, anytime you move a term, the symbol has to move with it, okay? So even though this was a plus sign, when I change the order, I now have a negative sign here because that's what was in front of my negative 7ab. Then we are going to find our factors of 6. So we have 1 times 6 and 2 times 3. And we have to figure out which of those will add to give us negative 7. Now, 1 plus 6 would give us positive 7. But I could turn both of these into negatives. If I do that, negative 1 times negative 6 is still 6. And now negative 1 plus negative 6 is negative 7. So we will replace our middle term with those factors. When we do that, we still keep both of these variables. So I now have negative 1ab minus 6ab, since these are both negative, and then plus 3b squared. Then we divide this in half, making sure that this negative sign still goes with the term behind it. And now I'm going to see what can I factor out of this. Well, The only number I can divide both of these numbers by is 1, and they both have an a, so I can also take an a out. 2a squared divided by 1a, well, 2 divided by 1 leaves me with 2, and a squared divided by a leaves me with a. Then negative 1 divided by 1 is just negative 1 still. A divided by a cancels out, and I'm left with my b. And then on this side, negative 6 and 3 are both divisible by either 3 or negative 3. Let's see what happens if I only take out a 3. And then both of these terms have a b, so I can take out a b as well. If I do negative 6 divided by 3, I'm left with negative 2, and that won't be the same as this. So instead, I'm going to turn this into a negative 3. Now if I do negative 6 divided by negative 3, I have a 2. A divided by, there's no a here, so I get to keep my a. And b divided by b will cancel out. And then 3 divided by negative 3 is negative 1, and b squared divided by b is b. Now my binomials are the same as each other, so I'll write that out. 2a minus 1b, and you could write that as just 2a minus b if you'd like. That one there isn't necessary. And then the stuff that was outside the bracket gets its own binomial, so 1a minus 3b. Again, that 1 there isn't necessary. You don't need it if you don't want it. But that is our final answer. The final type of special polynomial is something called a difference of squares. A difference of squares looks a little bit weird. It's only going to have 2 terms that are being subtracted. If there's a plus sign between them, it's not a difference of squares. And the squares part comes in because both terms are perfect squares. So difference meaning subtraction, squares meaning perfect squares. So this looks like something like this. We've got 2 terms that are being subtracted. 81 is a perfect square. The square root of 81 is 9. X squared is a perfect square. The square root of x squared is x. And 49 is a perfect square. The square root of 49 is 7. In order to start this, our very first step is going to be to create a b value so that we can use our ACB method. And essentially, we're going to add in a 0 as our b value. So add 0 as a b value. It also needs a variable. So what that would look like is I would keep my first term and then add a 0. And if this is an x squared, the variable is going to be an x. And then I keep my last term. Now that I've done that, I can follow the same kind of steps I've been doing all along. So multiply a times c. So in this case, it is 81 times negative 49, which gives me negative 3,969. Now, once again, we have to find factors of this that add to our b value. But with a difference of squares, it's really easy to find the right factor. Oopsies. -3969. The way we can find the factor of that adds to 0 is to just take the square root of it. If you take the square root of, actually we'll just ignore that negative sign for now. Take the square root of 3969 and you get 63. And so because of that, that tells us that 63 times 63 would be 3969. If I make one of them negative, I get negative 3969. And negative 63 plus positive 63 adds to 0, adds to our B value. So then we're just going to replace our B value with our factors. Like so. I've put them in this order just so my two negatives will be together and my two positive numbers are together when I split this in half. Then I'm just going to see what the biggest number I can divide both of these by is. And it turns out that they are both divisible by 9, and they both have x's, so I'll take an x out as well. 81 divided by 9 is 9. X squared divided by x is x. Positive 63 divided by 9 is positive 7, and x divided by x cancels out. We'll do the same on the other side. See what the biggest number that both of these can be divided by is. And it turns out that it is 7. And because these are both negatives, I will take out a negative 7. Negative 63 divided by negative 7 leaves me with 9. And because I don't have an x here, my x stays on the inside. Negative 49 divided by negative 7 is positive 7. Then we check that our brackets are the same as each other. They are, so I'll write it out. And then the leftovers will get their own bracket, 9x minus 7. The special thing about all difference of squares is that your last two binomials will be almost identical except for the sign. Okay. One's positive in the middle, one's negative in the middle. Other than that, they're the exact same. Compare that to our perfect square trinomial, where both of these were the exact same and we could write it as a power. This one cannot be written as a power because it's not quite identical. So that's our final answer. Okay guys, your homework will be posted on Google Classroom, so please make sure to check that. And I'll also be posting some review questions for you guys to work on for your quiz in a few days.